We are going to skip chapter 14 and go to chapter 15, which is on a chapter about chemical equilibrium. When you hear the word equilibrium, you should hear the word equal in there. And it's dealing with chemical equations, but up to this point, the total truth about chemical equations, which the equation also has the root of equal in there as well, the whole truth about chemical reactions and chemical equations hasn't been told to you. So we're going to add to your knowledge about chemical reactions today. So when you think about equilibrium, I hope you've heard that term before. It means to keep things in balance, much like an equation keeps things balanced, one side equals the other side. Well, with equilibrium, we're going to look at how there's more of a back and forth between reactants and products than you've been told about up until now. Okay, so we're going to look at reactions called reversible reactions. So if you think about the way a chemical reaction normally looks, you have your reactants on one side, you have the arrow, and then that points to what's produced, or the products. Well, what happens many times is that there's actually a back and forth. And so you have your reactants reacting to make your products, but at the same time, the products are breaking back down and reforming the reactants. And so the normal reaction, where you have the left side forming the right side, or the left side with the reactants forming the right side, the products, that is called the forward reaction. But then there's also the reverse reaction, where you go back to the original reactants. So we're going to look at that and how that goes back and forth with chemical reactions. So the way it really works is when you have a reversible reaction, meaning you're making products, but you're also remaking reactants, you have in your reaction vessel both the products and the reactants mixed together. And the reactants are going to react together to form the product. But at a certain point, the products are going to start reforming the reactants. And eventually, you're going to get to what's called, ideally, you're going to get to the equilibrium, where the amount of the reactant stays the same and the amount of the products remain the same. But meanwhile, the reaction is just going back and forth. So we're going to look at these in terms of ratios, and I'll get to those kinds of calculations in just a minute. But in reversible reactions, you have products and reactants in your container together as a mixture. And the ratio in which reactants and products are present in the mixture depends on how quickly these reactions proceed, both the forward reaction and the reverse reaction. And if you do something to the reaction that changes the rate of the forward reaction, which is what we think of as the normal reaction, or the reverse reaction, meaning you go backward toward the reactants, that's going to change the ratio of the products and the reactants in the mixture. And what we're going to do is we're going to look at these reactions, you're going to see what I'm talking about, and then we're going to go through different scenarios of what would change the outcome of these reversible reactions. So when you reach equilibrium, what that means is that the forward reaction and the reverse reaction are proceeding at the same rate. And in chemistry, when we talk about equilibrium, we're talking about changes that are in balance. The back and forth rates are the same. So how does this look? So look at what we're doing now. We're introducing this idea of the double arrow. Whereas, up until this point, you've just had the arrow pointing toward the products. But what's really happening in many, many, many situations is that you have your reactants. They do make some product, but at the same time, the products are reacting together to go back, okay, and then remake the reactants. Likewise, you can have phase changes that are in equilibrium. If you are right at that freezing and melting point, or in this case, evaporation point, if you are right there at the boiling point, you're going to have some back and forth between that liquid and gaseous state. And again, something else you're going to look at is aqueous solutions. If you put sodium chloride, which is a solid, into water, you're going to get a back and forth between the formation of ions and the formation of your crystalline solid. So we'll look at all these types of reactions. So if you have a reaction that displays some sort of equilibrium and the formation of the product is favored over the recreation of the reactants, then the concentration of the products is going to be higher at equilibrium. But likewise, if you have a reaction that doesn't really want to go to completion as much, that means that the reactants are going to be favored. So then the concentration of the reactants are going to be higher at equilibrium than the products. So in this case, you have sometimes, if you know, you can display it with the longer arrow pointing towards the favorable side, meaning this reaction where you take hydrogen gas and iodine gas and react it to form hydrogen iodide, this product is favored over the reactants. So the equilibrium is going to produce the reaction at equilibrium will result in as you can see here, a higher concentration of hydrogen iodide as compared to the reactants that you started with. So the way this works is over time, you have approximately equal amounts of your two reactants and no product has been made. So there's no amount, the concentration at time 0 of your product is also 0. And then you have the concentration or the amount of your reactants. They react together, they react together. As they react together, over time, as it starts, you start to make your product and the concentration of the product increases. And then once you establish equilibrium, there's still some back and forth, but it's favored to where that you're going to end up with a higher concentration at equilibrium of your product than you would the reverse reaction. So we're going to look at this in a generic way. We're going to look at something called an equilibrium constant. So just like we had constants with delta 8, where we have values that were determined for delta H and entropy and Gibbs free energy in chapter 13, there are also equilibrium constants that can either be found or have already been established. And we look at these equilibrium constants based on the reactants and the products that the reaction deals with. So if the forward reaction rate is the same as the reverse reaction rate, that means we are at equilibrium. And the way we figure that out, or the way we just establish what's called, ultimately the constant is going to be called KEQ, constant, just a K. And so this the equilibrium constant is if the ratio of the concentration, so these brackets right here refer to the concentration in molarity. So we're going to be talking about molarity. So it's going to be the concentration of the products over the concentrations of the reactants. And this KF and KR refer to forward reaction, meaning they're making the products, over the reverse reaction, meaning how much reactant do you have left. Okay, so we call this KEQ is called the equilibrium constant. Now keep in mind that it's the concentration of the products or the forward reaction over the concentration of reactants or the reverse reaction. So keep that in mind. Concentration of products over the concentration of reactants. Well, why does that matter? Because if you have an equilibrium constant that's greater than 1, that means your numerator, which has your concentration of your products, if it's KEQ, then the concentration of the products is going to be greater than the concentration of the reactants. So the forward reaction, the normal, what we think of as the normal reaction, is the predominant reaction. If the KEQ is less than 1, meaning that at equilibrium, you actually still have a higher concentration of your reactants, then the reverse reaction is favored. And we use the stoichiometry, meaning the balanced chemical equation. We use that to determine the equilibrium constant. So let's take another generic reaction. And this was covered in the video too. So this is just a reminder from the other video. All right, so here is our generic chemical equation, where the lowercase letters are the coefficients and the uppercase letters are the substances. All right, so the reactants, A and B, the products, C and D. Now remember, it's the concentration of the products over the concentration of the reactants. So watch what we do. We take our products, which are capital C and lowercase d, we're going to multiply them together. But before we multiply them together, we raise the individual concentrations by the coefficient of the balanced equation. So the concentration of C raised to the C power, because the lowercase c is replacing our coefficient. So if that were a 2, if lowercase c were a 2, it would be the concentration of C squared. Likewise, D is another product. We're going to raise it to the lower D power, and we're going to divide that by the concentration of capital A reactant raised to the lower A power, because that's its coefficient. And then we're going to multiply that by the concentration of reactant B raised to the lower B power. So to finish things up today, we're going to wrap it up with the law of chemical equilibrium. So at a fixed temperature, a chemical system may reach a point at which the ratio of the concentration of the products to the reactants is constant. So when everything takes place again at a certain temperature, probably everything's going to be based off of 25 degrees Celsius. So at a fixed temperature, a chemical system may reach a point at which the ratio of the concentration of the products and the concentration of the reactants is a constant. And that's going to be our KEQ value. We can either calculate it if we have enough information, or many times we can look it up in a chart. And I will stop there today. We will pick up tomorrow talking about homogeneous and heterogeneous equilibria. Have a great day.